Hello, everybody. Thank you so much for coming out tonight on this Tuesday evening for some science on screen. A big round of applause for the folks at the Sloan Foundation for putting on this great show for us. We've got a wonderful series. This is the first film in our series. So the Sloan Foundation is really committed to promoting science education and has teamed up with art house cinemas around the country to connect the cinema that we know and love so much with the research that's being done by some of our most illustrious scientists from around the country. So today you're here to watch Oppenheimer. Any folks see it when it first came out? Did anybody Barbenheimer on the day? I know I did. So we're so glad to bring Oppenheimer back. And I'd love to introduce our speaker for today. Dr. Jacob Barandes is a theoretical physicist and philosopher of science at Harvard University. He's joining us via Zoom from Boston. He currently serves as a lecturer and co-director of graduate studies for a physics PhD program, where he teaches courses on the fundamentals of theoretical physics, electromagnetism, general relativity, and the history and philosophy of quantum mechanics. He's also associated faculty with the Department of Philosophy. So there's going to be some really interesting conversations around this. So Dr. Barandes, are you with us? Can you hear us okay from Boston?
I am with you. Can you hear me?
Yeah, you're sounding good. I'm going to pass it
Excellent.
off. Please give a round of applause for Dr. Barandes for joining us. And if you have a few minutes, if you have any questions, hold on to them, and he can stick around for a couple of minutes and answer some questions. But take it away, Dr. Barandes.
Thank you very much. Thank you for the wonderful invitation. I'm very happy to be here and talking to all of you this evening. There's a lot I want to talk about, so I'm going to get started. And again, as Atalia said, I can stick around and answer a few questions at the end of the presentation. Everyone hear me okay?
Sounding good from Orange County.
Excellent. All right, let's get started. So my talk is called Oppenheimer, Quantum Mechanics, and the Structure of Reality. So I have two sides. This is just a little bit about me. One side is what I call philosophical physics. That means that I use the methods of analytic philosophy to apply rigorous scrutiny to our best, most successful physical theories. So, for example, looking for cracks in our theories that may contain surprises and new discoveries, pushing our theories to their logical limits, and putting the brakes on wildly speculative claims. There is a distinguished history to this approach to thinking about physics. Heisenberg, whom we'll be talking about a little bit later, Werner Heisenberg, talked about how philosophy is what directed him into physics in the first place. Albert Einstein had read all of Kant's critiques by the time he was 16, took courses in philosophy of science, ran a philosophy of science book group, and studied the works of Schopenhauer and Spinoza and Kant throughout his life. Many of the great debates about the fundamentals of physics became debates about epistemology, ontology, and fundamental questions in philosophy. Many of the people who brought us quantum mechanics and general relativity were deeply steeped and trained in philosophy, and there were strong connections between the physicists of the first half of the 20th century and many people working in the analytic tradition in philosophy, especially the Vienna Circle. I also work in what I call physical philosophy, which is investigating what our physical theories bring to bear on traditional questions in metaphysics, like what do our physical theories tell us about time, about locality, about probability, about causality. Okay, so here's an outline of what I'm going to be talking about this evening. I'm going to start by talking briefly about the myth of Prometheus and explaining the connection between that myth and Oppenheimer. Then I'm going to talk about the science of quantum theory. And then I'm going to talk briefly about the people behind the atom and the atomic bomb. All right, let's start with the myth of Prometheus. So why am I mentioning the myth of Prometheus? Well, the film Oppenheimer is based on the 2005 biography American Prometheus, The Triumph and Tragedy of J. Robert Oppenheimer by Kai Bird and Martin Sherwin. This is not the first time the metaphor of Prometheus has appeared in the title of a book. So this is Mary Shelley. Mary Shelley famously wrote the book Frankenstein, which was also titled Or the Modern Prometheus. This is a picture of Boris Karloff playing Frankenstein's monster in the film Bride of Frankenstein. So the idea of a scientist bringing the knowledge or power or magic of the gods down to humanity is an old idea and has inspired other works. Okay, so in her 1942 book Mythology, Edith Hamilton, uh, uh, referring to work by earlier Greek scholars, tells the story of Prometheus. As she tells it, the world was ready for the appearance of mankind. It was time for men to be created. Some say that the task of creating men was delegated by the gods to one of the Titans, Prometheus. Prometheus was a Titan. The Titans were actually the enemies of Zeus and the more familiar Greek gods. But Prometheus had actually sided with Zeus in the war with the Titans and was rewarded by not being sent to live under a giant mountain. And as the legend goes, Prometheus was given the task of creating man. Prometheus wanted to give man a way to be superior over the animals. So what Prometheus did was shape humans to be upright like the gods. And then Prometheus went to heaven to the sun. He lit a torch and brought down fire, a protection to men far better than anything else, whether fur or feathers or strength or swiftness. And this is a painting, Prometheus Brings Fire to Mankind, from 1817. So Zeus unfortunately forgets that Prometheus had helped conquer the other Titans. Zeus was very angry that Prometheus had brought fire to humans, so he had his servants, force and violence, seize Prometheus and take him to the Caucasus, where they bound him to a high-piercing, headlong rock in adamantine chains that none can break. Adamantine was a material that was unbreakable, and this is a sculpture called Prometheus from 1762, where you can see that an eagle, red with blood, every day tears at Prometheus's liver, and his liver grows back every night, and this goes on for eternity. The film is not subtle about this connection. In the opening to the film, we see the epigraph, Prometheus stole fire from the gods and gave it to man. For this, he was chained to a rock and tortured for eternity. Okay, I'm going to move now to talking about the science of quantum theory. I'm going to see if I can move the ribbon. There we go. Okay, this ribbon, I'm just going to move it a little bit because I can see my slides. Okay, so this is a very famous picture from the fifth Solvay conference. The Solvay conferences were gatherings of physicists in Brussels. The fifth one took place in 1927. This was the final year when Robert Oppenheimer was in Europe studying quantum mechanics. So this was the atmosphere that Oppenheimer found himself in. This is a very famous photograph. You find this photograph in physics departments all over the world. And this photograph, it's famous because so many of the people who played central roles in the development of quantum mechanics appear here. So I can actually use this photograph to tell a little bit about the history of the development of quantum mechanics. The story, in some ways, begins in 1900 with Max Planck. Max Planck was trying to understand experiments that were being done with objects called blackbodies. These were chambers that were heated and radiation, light came out of them, electromagnetic radiation came out of them, and people could measure how strong the different colors were. Some colors were stronger than others, brighter than others, and as the temperature of the blackbody was increased, more brightness came out. The overall amount of brightness that came out was greater, but which colors were the brightest also shifted. And there was a very particular pattern of which colors had which levels of brightness given temperature. And Max Planck was the first to explain on theoretical grounds why you had that spectrum of radiation. To do it, he had to imagine that energy came in discrete or quantized amounts, which were called quanta, and this began quantum theory. This is where the quantum and quantum theory began. He called this idea the quantum hypothesis. That's Marie Curie, who worked on radioactive elements, discovered polonium and radium, and did major work on the development of radioactivity, which she named. between 1898 and 1902. She is the only person in this picture to have won two Nobel Prizes, to ever have won two Nobel Prizes. She had won both of them by the time this picture was taken, one in chemistry and one in physics. She's still the only person to have won two Nobel Prizes in the sciences in two different fields. That's Albert Einstein. Albert Einstein made many major contributions to physics, too many to list here. But the most salient for quantum mechanics is that in 1905, he discovered the photoelectric effect. He was able, well, it was a known observation, but he provided a theoretical explanation for it in terms of energetic quanta of light being absorbed in discrete amounts by electrons and materials. And providing this explanation was able to account for the very strange features of the photoelectric effect. That's Niels Bohr. Niels Bohr we'll have more to say about later as well. Niels Bohr played a central role in the development of quantum theory, especially in the era of the old quantum theory that reigned from 1900 to 1925. His most famous contribution to this was the development of a model of the hydrogen atom. It is today considered a fairly rudimentary model, but it was the first model that gave an explanation and a derivation for certain features of this model and won him eventually the Nobel Prize. This model he proposed in 1913. That's Arthur Compton, who discovered Compton scattering in 1923. Compton scattering played a central role in understanding the relationship between particles and waves. That's Louis de Broglie, who in 1924 proposed a more detailed duality or relationship between particles and waves. And that is Werner Heisenberg. Again, I'll have more to say about Heisenberg later in this talk. Heisenberg introduced the first modern formulation of quantum mechanics in 1925. It was called matrix mechanics, or at least that's what it was called by his advisor, Max Born, who I'll point out in a moment. Max Born is sitting directly in front of him in this picture. It is difficult to explain just how important Heisenberg was to the development of modern physics and quantum mechanics. In addition to developing the first modern formulation of quantum mechanics, which brought to a close the old quantum theory and initiated the era of modern quantum theory in 1925, he's also very famous for introducing the uncertainty principle in 1927. He was a towering figure in physics, truly extraordinary. That's Wolfgang Pauli, played a central role in the development of quantum mechanics, is most famous for introducing the exclusion principle, which provides an account for why all the electrons in an atom don't all shrink down to the lowest energy level. The exclusion principle explains why chemistry works, why outermost electrons stay outermost and can participate in chemical reactions, among many other contributions that he made. That's Erwin Schrödinger of the famous Schrödinger cat thought experiment. His major contribution was introducing the wave function. This was an extension of de Broglie's wave-particle idea to provide a precise mathematical formalism for using the waves of quantum theory to make predictions. He introduced this idea in a paper describing what he called an undulatory theory of mechanics in 1926. And there's Max Born, whom I mentioned before. Max Born worked with Werner Heisenberg and Pascual Jordan, who's not pictured here, to develop matrix mechanics. Max Born, among many things, is famous for introducing the statistical interpretation of the wave function, the idea that Schrödinger's wave functions should be understood as giving probabilities for measurement outcomes. That was in 1926. That's Paul Dirac. Paul Dirac took all of the ideas that were developing at this time, contributed some of his own, and put together the first axiomatic complete framework for modern quantum theory in a book called Principles of Quantum Mechanics he published in 1930. He went through an incredible period of scientific innovation, and over a period of about 20 years, just produced paper after paper, all single author, introducing some of the most important ideas in physics. I just mentioned here that one of his contributions was the notion of a path integral or sum over paths, which is more widely associated with Richard Feynman, who I'll mention later. Okay, I'm going to play a video now just to show what these people were like in real life. So I'm going to stop sharing this screen. Hold on. And I'm going to reshare. Okay, so let me now shift back to Zoom and share. All right. Natalia, can you confirm everyone can see?
Yeah, confirmed over here.
All right. And let me know if you can also hear the sound.
The film opens with quick shots of
Can you all
Erwin
hear?
Schrödinger and Niels Bohr.
Good.
Auguste Picard of the
This is
University of
that
Brussels
Copenhagen,
follows,
this is that
and then the
Solvay
camera
conference.
refocuses on Schrödinger and Bohr. Erwin Schrödinger and Niels Bohr, followed by Picard. Schrödinger, who developed wave mechanics, never agreed with Bohr in quantum mechanics, nor with Werner Heisenberg's uncertainty principle. Solvay gave Heisenberg an opportunity to discuss his new theory. Here's French physicist Léon Brillouin, Hendrik Kramers, Bohr's former assistant, and Paul Dirac talking with Max Born, whose statistical interpretation of the wave function ended determinism in the atomic world. These men, Bohr, Heisenberg, Kramers, Dirac, and Born, together with Wolfgang Pauli, represent the founding fathers of quantum mechanics. On the other hand is Louis de Broglie, who wrote his dissertation on the wave nature of matter, which Schrödinger used as the basis for wave mechanics. The owner of the camera, Irving Langmuir, is seen chatting briefly with Bohr. At Solvay, Bohr refined his thoughts on complementarity and sparred with Einstein over the implications. Here he's with Paul Ehrenfest. Kramers' work in Copenhagen on dispersion theory was essential to the development of quantum mechanics. Langmuir, an American chemist at the GE lab in Schenectady, hence the camera, had recently broken his leg and appears to explain to Ehrenfest how he gets around. By 1927, Dirac in the middle had independently developed quantum mechanics and made other significant contributions, as had Wolfgang Pauli, who formulated the exclusion principle. A lively Madame Curie, Born and Pauli working out a problem. Note the changed demeanor as the participants exit from the meeting, except for the smiling William Lawrence Bragg and Peter Debye, Arthur Holly Compton, Owen Richardson, Max Born, Madame Curie, Hendrik Kramers, H.A. Lawrence, Paul Langevin, Albert Einstein, whose famous response to Born and the statistical interpretation of the wave function was, "God does not play dice." Bohr, Planck, Pauli, and Belgian soldiers, a portentous conclusion.
Be sharing my slides. Okay, can everyone see my slides? Yeah, I wanted
Yep.
to. It's incredible that we have video footage of that Solvay conference in 1927. It's remarkable to see all of those important figures in the flesh, as Oppenheimer would have seen them. These are the people of the older era of physics, and in the film, you'll hear Oppenheimer and Einstein talking about that older period in physics. Okay, I'm going to see if I can move this ribbon a little bit so I can see. Good, okay. So Oppenheimer learned quantum theory in Europe in the period 1925 to 1927. The film talks about how there was very little going on with quantum mechanics in the United States at this time. Oppenheimer was very explicit about wanting to go to Europe, where he thought the development of this theory was happening. He was in his early 20s at the time. And just as a personal anecdote, I started learning quantum theory when I was in college over a summer in Paris with the woman, Shelley, I would later marry. This is a scan of some of my handwritten homework from that time that I was doing over that summer in Paris. To this day, yeah, thoughts of and memories of baguettes and accordion music come to mind when I think about quantum mechanics. It's a very nice pairing. Okay, moving on. This is a very brief introduction to quantum theory in one slide. I only have a couple of minutes here to tell you about quantum theory. I would need at least 10 to explain the theory completely, and I don't have that, so we'll just do it in a minute. I'm going to break it down to basically two principles. One, a quantum system, for example, an atom or subatomic particle, is represented according to quantum theory by a mathematical thing called a quantum state in an abstract space called a Hilbert space of some number of dimensions. Right. Now that might seem very abstract, and it is. It is extremely abstract. There's no question about it. The quantum state of a quantum system can, in some cases, resemble a wave, and this is the thing that Schrödinger described with a wave function. The space where these quantum states live, a so-called Hilbert space, involves mathematical abstractions called complex numbers. Complex numbers are generalizations of ordinary numbers, but can include the strange square root of -1. So you may remember from high school mathematics that when you multiply a positive number times a positive number, you get a positive number. But if you multiply a negative number times a negative number, you also get a positive number. And that would seem to indicate the square root of that you can only take square roots of positive things, because a square root is by definition a thing that times itself gives you something else. How can you take a square root of a negative thing? How can anything times itself be negative? Those are called imaginary numbers, and when you combine them with ordinary numbers, you get what are called complex numbers. So Hilbert spaces involve these complex numbers. They are definitely very abstract things. And when I say some number of dimensions, these can be very high or even infinite dimensional, so much higher than the 3 dimensions of ordinary physical space. Hilbert spaces don't seem to have much to do with the physical space that we move around in. And yet this is the place where the mathematical quantum states exist, at least mathematically. The second principle is that when the quantum system is measured, and I've got a bunch of question marks here, reasons I'll explain in a moment, there's a rule attributed to Max Born, the Born rule, that he proposed in 1926, that takes in the quantum state and predicts the probabilities of the various possible measurement outcomes. This is the sense in which quantum theory makes predictions about probabilities. And then, right after the measurement is done, the quantum state collapses, again a bunch of question marks, to lock in that outcome. So if the same property is measured again, with nearly perfect certainty, you're guaranteed to get the same result. Just as an aside, Max Born, just as one of those historical curiosities, was the grandfather of Olivia Newton-John. So for those of you who know who that is, interesting historical anecdote. So there's a question that arises immediately. What counts as a measurement? When is something a measurement and when is it not a when is it not a measurement? Does it have to be a person doing the measurement? Could a robot do a measurement? Could a cat do a measurement? Could a bacterium do a measurement? Could a virus do a measurement? Like when does a particular process count as a measurement? We think very extremely small things like individual electrons cannot do measurements. People can do measurements. And it's very strange that this seemingly fundamental theory of microscopic phenomena seems to rely in such a basic way on an undefined notion like a measurement. And this is called the measurement problem. Another question is the collapse of the quantum state something physically happening out in the world, or is it merely something that we do in our minds to lock in what we know the answer to be? These are outstanding questions in the foundations of quantum mechanics. And if they seem not as profound as maybe they look, trust me, people have been working on these problems for decades. And there are many plausible solutions to these problems. But when you sit down and actually try to nail down all the mathematical details, you often run into trouble. And then at a larger level, how do we account for the category of non-measurements that seem to be going on all around us? We look around and we see birds flying around. We see kangaroos hopping. Early universe astronomers look in their telescopes and measure the properties of gases mixing in the early universe. People fall in love. The seasons change. These things don't seem to be measurements in any obvious sense, and yet they seem to be happening. Are we saying that these are not accountable by quantum theory, or does quantum theory somehow account for them in ways we don't yet fully understand? There's a category problem that also one deals with in quantum theory. We're not going to be able to answer all these questions, but I just figured I would take this moment as someone who works in philosophy of physics to point out that quantum theory is in some ways still a work in progress. Nonetheless, these two principles are the basis of what Oppenheimer was studying, and that laid the groundwork for the development of the atomic bomb. Okay. Watching the film, I was struck by how it visualizes Oppenheimer's experience learning and thinking about quantum theory. And I say this because when I was learning quantum theory, and you was learning about things like these abstract Hilbert spaces, there were images that came to my mind. The things that show up in quantum theory are often very difficult to visualize, but yet one does sometimes have visuals that can seem very abstract and hard to explain. I thought it was remarkable how the film attempted to get across what it's like to engage with and encounter quantum theory. So here are just some of the images that show up in the film. Some of these from early on in the film, depicting things that were going on in Oppenheimer's mind as he was learning about quantum theory. And some of these images also happen later in the film as Oppenheimer thinks about or talks to people about quantum theory. The images are intended to be abstract, but I think they're supposed to evoke atoms or stars or just abstractions happening in high-dimensional spaces that are difficult for us to visualize. I just thought it was remarkable how many of these images show up in the film. This image in particular is supposed to depict the chain reaction, the nuclear chain reaction. Okay, so that was interesting. All right, so now we're at the third part of the talk. I'm going to talk now about the people behind the atom. First and most obviously is J. The J is for Julius, Robert Oppenheimer, or Oppie, as he was called by his colleagues and friends. He lived from 1904 to 1967. So he was, again, visiting Europe and learning about quantum theory during his early 20s. And the beginning of the film, when you're seeing him as a young man in Europe, that's when he's in his very early 20s. Robert Oppenheimer is portrayed in the film by Cillian Murphy. You can see they got the hat and the cigarette. Oppenheimer was born to a wealthy family in New York City in 1904. He got his undergraduate degree in chemistry from Harvard in 1925, and that's when he went to the University of Cambridge before eventually going to Germany, to Göttingen in 1927, and he studied under Max Born, the same Max Born who was also one of the advisors to Heisenberg and introduced the statistical interpretation of quantum theory. Oppenheimer made major theoretical contributions not only to quantum theory, but also to general relativity. He's widely regarded as the father of the atomic bomb, and I won't have very much to say about him here because, after all, the film is about him. But I do want to tell one anecdote about his time in Göttingen. This is from Max Born's remarkable autobiographical memoir, My Life: Recollections of a Nobel Laureate. This is what Max Born wrote about Oppenheimer. This is in 1926 when Oppenheimer was relatively new to Göttingen and taking classes there, one of which was taught by Max Born. Max Born writes, Oppenheimer caused me greater difficulty. He was a man of great talent, and he was conscious of his superiority in a way which was embarrassing and led to trouble. In my ordinary seminar on quantum mechanics, he used to interrupt the speaker, whoever it was, not including myself, and to step to the blackboard, taking the chalk and declaring, "This can be done much better in the following manner." I felt that the other members did not like these perpetual interruptions and corrections. After a while, they, the other students, complained. But I was a little afraid of Oppenheimer, and my half-hearted attempts to stop him were unsuccessful. At last, I received a written appeal. I think that Maria Gerpert, then a very young student, now a well-known professor in California, was the driving force. They gave me a sheet of paper, looking like parchment, in the style of a medieval document, containing the threat that they would boycott the seminar unless the interruptions were stopped. I did not know what to do. At last, I decided to put the document on my desk in such a way that Oppenheimer could not help seeing it when he came to discuss the progress of his thesis with me. To make this more certain, I arranged to be called out of the room for a few minutes. The plot worked. When I returned, I found him rather pale and not so voluble as usual, and the interruptions in the seminar ceased altogether, but I am afraid he was deeply offended, though he never showed it and gave me a splendid present before he left, a first edition copy of Lagrange's Mécanique Analytique, which I still possess. But I was never again invited to the USA, in particular not to Princeton after the end of the Second World War, when every theoretical physicist of any standing spent some time at the Institute of Advanced Study, whose president Oppenheimer had become, as we'll see in the film. But this is only a conjecture, and it's quite possible that neither his influence nor his rancor was as great as I imagined. Maybe the reason for my being neglected was the well-known fact that I was opposed to atomic weapons and criticized those who made them. It just gives a certain window into Oppenheimer in his young years and his reputation there. All right, I'm going to play a video with the real Oppenheimer. So I'm going to stop this screen share, and I'm going to reshare. This is a video of Oppenheimer as an older man talking. Let me just reshare my screen. All right, starting the video.
Looking back now, do you think that our country's use of the bomb was necessary?
I believe that the view which I learned from many, but above all from General Marshall and from Colonel Stimson, the Secretary of War, the view that they had that we would have to fight our way to the main islands, and that it would involve a slaughter of Americans and Japanese on a massive scale, was arrived at by them in good faith, with regret, and on the best evidence that they then had. To that alternative, I think the bomb was an enormous relief.
Okay, I'm not going to play the entire video, but it gives you a sense of Oppenheimer and his views on the bomb. I'm going to play one more, which is very salient to the film because it comes up in the film. I'll play it, and then you'll see why.
We knew the world would not be the same. Few people laughed. Few people cried. Most people were silent. I remembered the line from the Hindu scripture, the Bhagavad Gita. Vishnu is trying to persuade the prince that he should do his duty, and to impress him takes on his multi-armed form and says, "Now I am become death, the destroyer of worlds." I suppose we all thought that one way or another.
Stop the share and return to our presentation. All right. Another key figure is Niels Bohr. Niels Bohr also shows up in the film. Niels Bohr lived from 1885 to 1962. Here's a picture of Niels Bohr and another picture of Niels Bohr having a discussion with Einstein. They seem to be having a good time. Niels Bohr is portrayed in the film by Kenneth Branagh, and we see him pretty early on in the film. Bohr was born in Copenhagen, Denmark in 1885, got his doctorate from the University of Copenhagen in 1911. He was a major figure in the development of the old quantum theory. Again, this is the collection of heuristic, approximate formulas that made predictions. They weren't always exactly right. They didn't fit together into a comprehensive framework just yet. He made major contributions to its development, and in particular, proposed a model of the hydrogen atom that made remarkably good predictions and won him the 1922 Nobel Prize. Bohr was widely regarded as having a kind of intrinsic understanding of quantum theory that transcended the mathematics. People would go to him and talk to him, and he just had this way of understanding quantum theory that was organic. It was like baked into his brain, and he could explain things and make predictions without using mathematics. It was really very remarkable. People regarded him as a prophet almost. This is Werner Heisenberg. We've encountered a few times already in this talk. So he's portrayed by Matthias Schweighofer in the film. We see Heisenberg pretty early on. Oppenheimer meets Heisenberg. There's clearly a meeting of minds there. He was born in Würzburg, Germany in 1901, got his doctorate at the University of Munich in 1923. He then went to Göttingen, where Max Born was, and worked with Max Born. The story goes that he developed a very, very bad case of hay fever in the spring of 1925 and went to an island called Heligoland with much lower levels of pollen. And there, apparently, he had intended to memorize a lot of Goethe and figure out quantum mechanics, putting together all the formulas and complicated equations that had been developed up until that time. He accomplished at least one of those tasks. He came back with a comprehensive formulation of quantum theory. It is one of the most brilliant papers in the history of science. It is a paper I assign my students to read. It is a work of staggering genius. He also formulated the uncertainty principle in 1927. He won the Nobel Prize in 1932 for his work on quantum mechanics, and he made many other extremely important discoveries in physics. He stayed in Germany during the war, and although he never joined the Nazi Party or espoused Nazi ideology, he did lead their atomic bomb project, although he argued for most of his life after the war that he had tried to hold back their project. There's been some historical dispute over whether that was true. In the film, we also meet pretty early on Isidore Isaac Rabi. He lived from 1898 to 1988. He's portrayed by the actor David Krumholtz in the film. We see a lot of him in the film. He was born in Galicia in 1898. This is today a region on the border with Ukraine and Poland. He came to the US as an infant, was raised in New York City, got his undergraduate degree in chemistry at Cornell in 1919, and his doctorate in physics at Columbia in 1927. He won the Nobel Prize in 1944 for his work on nuclear magnetic resonance. This is the science that underlies MRI scans, which are magnetic resonance imaging scans. Actually, they are nuclear magnetic resonance imaging scans, but they usually don't put the N for nuclear there because they don't want to scare patients. Right, I'm going to show a quick video of Rabi. Rabi plays such an important role in the film, I thought it would be useful to see what he was like in real life. So this will be a brief video. All right, let me share my screen. All right, so playing.
Isidore Rabi is now 85 years old, a Nobel Prize winner. He came back to Los Alamos this spring for the laboratory's 40th anniversary. He came to speak to a new generation of scientists. What goes through your mind now when you come back?
Sorrow that the place still exists.
You didn't expect it to be here this long?
Certainly not. It's all extraordinary.
Many of the first Los Alamos scientists thought atomic weapons would be banned after the war. They had, after all, been present at creation.
I'm going to stop there. Let me reshare my slides. That's the real I, Rabi. We also see Einstein in the film a couple of times. So here's Albert Einstein, born on Pi Day. I think that's somehow fitting. March 14th, 1879, died in 1955. There he is as a young man and toward the end of his life. He's portrayed in the film by Tom Conti while he is at the Institute for Advanced Study, where he spent the last part of his career. He was born in Ulm, Germany in 1879, got his doctorate in physics at the University of Zurich in 1905. And what is there to say about Einstein? I mean, one would have trouble listing all of his contributions. Most famously, he's associated with his special and general theories of relativity. General relativity is still our cutting-edge theory of gravity, our fundamental theory of gravity, and is still used to understand black holes and the universe, among many other things. He won the Nobel Prize in 1921 not for his work on relativity, but for his contributions to quantum theory, in particular for his 1905 work on the photoelectric effect, which I mentioned earlier. And he spent the last stage of his career at the Institute for Advanced Study at Princeton. I don't have much more to say about Einstein. Einstein's pretty well known, so probably people know a lot about him. I am going to show one very brief video of him, and this will be the last video I'll show in this presentation. Okay, so this is Einstein speaking. This was the real Einstein, at not too far away from the time when he's portrayed in the movie.
We are concerned here with an act of humanity, with the maintaining of cultural values, and not least with a measure of considerable political importance. The effect upon all nations, and not least upon the Germans, of the fate of these innocent people, so maliciously persecuted, must not be underestimated.
That's the real Einstein. All right, so going back to our presentation. All right. So I wanted to say a few things about Kurt Gödel as well. Kurt Gödel shows up in the film. There's a scene in which, here he is, he's portrayed by James Urbaniak. He's portrayed walking in the woods with Albert Einstein, and these walks really did happen. In fact, they've become very famous. The walks with Einstein talking with Gödel. Seeing these walks portrayed in the film was really remarkable for me because I'd heard many stories about them but never seen them depicted visually. Gödel was born in Brunn, Austria-Hungary, now the Czech Republic, in 1906. Got his doctorate at the University of Vienna in 1929. He proved two theorems, his famous incompleteness theorems, Gödel's incompleteness theorems in 1931, that demonstrated fundamental limitations to the reach of mathematics. These theorems are so important and so famous, they've been described by many people as pieces of immortality, that after all of our present civilizations are gone, if anyone knows anything about mathematics, they'll still know these theorems. His theorems showed, there are two theorems. The first showed that any system of mathematics rich enough to contain arithmetic, which certainly seems to be the kind of mathematics we care about, will contain statements that may be true but are impossible to prove within that framework. And this means that the goal set forth by people like David Hilbert of Hilbert spaces, that one day we would be able to prove all statements, that is impossible. There will exist true statements that we'll never be able to prove within any axiomatic system. His second theorem said that you can't even show that any axiomatic system is fundamentally consistent. There's a famous story from 1947 when he went for his US citizenship exam, in which he claimed to have found a logical inconsistency in the Constitution that he said would allow the United States to become a dictatorship, something he was very nervous about given his own background and his escape from dictatorship in Europe. He joined the Institute for Advanced Studies and took many long walks with Einstein, with whom he'd become a very good friend. Richard Feynman also shows up in the film. Here's, on the left is Feynman's photograph for when he was at Los Alamos, and next to that is a photograph of him with his famous bongo drums, which feature in the film. If you're paying attention, you'll see there's a party with someone playing the bongo drums. That's Richard Feynman. He's portrayed by Jack Quaid in the film. We see him a couple of times in the film. We don't hear very much from him, though, in the film. He was born in New York City in 1918, got his undergrad degree at MIT in 1939, got his doctorate from Princeton in 1942, in which he turned Paul Dirac's sum on paths formulation of quantum mechanics into a powerful mathematical tool for making predictions. He won the Nobel Prize in physics in 1965 for something called renormalization in quantum field theory, which is a set of techniques for extracting reliable predictions from quantum field theory in the midst of what seemed like various mathematical problems. We see a lot of Edward Teller in the film. Edward Teller lived a very long time, 1908 to 2003. This is the real Edward Teller. On the left is his picture from Los Alamos. On the right is a picture of him when he was somewhat older. He's portrayed in the film by Benny Safdie. I want to go into too much detail about his portrayal in the film, but they do show him suggesting there could be a very serious problem with the chain reaction that could be produced by nuclear power and nuclear weapons. He's also famous for his development and advocacy for the super, or the fusion bomb, or the hydrogen bomb. He was born in Budapest, Austria-Hungary in 1908, got an undergraduate degree in 1928, doctorate from Leipzig in 1930, studying under Heisenberg, and again, widely regarded as the father of the hydrogen bomb. There's a quotation from Rabi, I think, who said that the world would have been a better place had Teller never lived. We see a couple of other important figures in the film. I'll run through these somewhat more quickly. We see Ernest Lawrence, an experimental physicist. Here he is. He lived from 1901 to 58. He's portrayed by Josh Hartnett in the film. He was an experimental physicist who won the Nobel Prize in 1939 for inventing the cyclotron, an early particle accelerator, and we see some discussion about this in the film. We also see Enrico Fermi. Enrico Fermi was an Italian-American physicist. Here he is. He lived from 1901 to 1954. He's portrayed by Denny De Ferrari in the film. He won the Nobel Prize in 1938 for his work on induced radioactivity by neutron bombardment, and he was instrumental in the realization of the nuclear chain reaction. We see Hans Bethe in the film. He's portrayed by Gustav Skarsgård. Hans Bethe lived a very long time. He had an illustrious career. He was a powerhouse of calculation. He was famous for being able to do extremely difficult, very long calculations. He ended up winning the Nobel Prize in 1967 for his work explaining and understanding the theory behind how stars create heavy elements, a process called nucleosynthesis. This is Leo Szilard. He shows up a couple of times in the film, in particular, trying to get Oppenheimer to sign an open letter opposing the use of nuclear weapons. He's portrayed here in the film by Made Hauman. And he developed the idea of a nuclear chain reaction in 1933 and also helped write a letter along with Einstein advocating for the United States government to develop nuclear weapons, something he eventually came out against later in his career. We also see Lily Schwenk-Hornig a few times in the film. She's portrayed by Olivia Thirlby. She was a scientist at Los Alamos. She participated in the development of the atomic bomb, and she became a strong advocate against the use of nuclear weapons. After the fall of Germany, and we see this in the film, she pushes for the atomic bomb to not be used in Japan, or at least only to be used on an uninhabited island as a demonstration. And this is rejected by leaders at the time. So if you're ever wondering, did people consider doing a test run of the bomb before dropping it on a populated city? Not only people considered it, but some people had actually strongly advocated for it. And finally, this is Leslie Groves. Leslie Groves is depicted in the film by Matt Damon. He was the military leader of the Manhattan Project, of the project at Los Alamos to develop the bomb. All right. And so the last thing I'll just say is be on the lookout for Klaus Fuchs, who shows up in the film. For those of you who know who Klaus Fuchs is, you'll know why I'm saying this. And for those of you who don't, I don't want to give any spoilers, but do pay attention to his appearance in the film. All right, that's it. Thank you and enjoy the film.
Thank you so much, Jacob, for joining us. You know, it's quite a long film, so we're going to just jump it right in and get started. But thank you so much for joining us, and have a good night's sleep out there in Boston. And we'll see you next time. Thank you so much. Oh, sorry.
You're very welcome.
We have time. Sorry, we have time for one question.
One question, please. Go ahead.
Okay. All right. Any questions from the audience before we dive in and get started? Any questions? I would like to know more about what happened in Paris, but that's for another time, I'm sure. Do you have your hand up, sir? Oh, okay. Hold on. We got an actual question here. Go on. Go ahead.
Is there any way you can do a real simple explanation of like the double slit experiment?
I'm glad you asked. So the double slit experiment shows up in, the very early days of quantum theory. It's a generalization of an earlier experiment that was done around the turn of the 1800s called the Young double slit experiment with light. It was proposed that if the experiment was done with a single electron, then you would be able to see wave-like properties of the electron. So I can give a very brief explanation of how this was supposed to work. The experiment was predicted long before it was actually done in the 1960s. It was first actually carried out in the 1960s. One sets up a wall, and in the wall are two small holes. An electron is sent toward the holes from an emitter, one at a time. One electron is sent at a time. And sometimes the electron will just bounce off and not go through the hole. Sometimes it will go through the holes. So at least that's what we think happens. And then there's a screen, a detection screen at some distance on the other side of the wall. So that as electron goes through one at a time, when it goes through the holes, it will be detected on the screen at some point after it has transited the distance between the wall and the screen. Every time this experiment is run, you get a dot that shows up on the screen, just one dot. You send an electron in. Sometimes it doesn't make it through the holes at all, but if it does, you get a dot. And you run this experiment over and over and over again, thousands of times, 10,000 times. And when you're done, you see that the dots are arranged in a very curious pattern. If we had been doing this experiment with, let's say, small pebbles, little rocks, throwing them at, I guess, a much bigger screen with holes in it, we would expect to see a cluster of rocks near the center of the detection screen, most of them landing somewhere near the middle, and then fewer and fewer of them landing as you go farther away. And so we would expect to see a dense concentration of dots near the middle of the screen and then very few farther away. That's if the experiment's done with stones, with pebbles, with classical objects, the objects that would be described by Newtonian physics. When you do this experiment with electrons, again, sending them one at a time, and you look at the dots, what you find is that after doing the experiment thousands of times, 10,000 times, the dots do not cluster near the center, and then they're fewer and fewer as you go away. Instead, the dots cluster in bands, you get distinct bands. You get distinct regions with lots of dots and then very few, and then lots of dots and then very few, lots of dots and very few. And it does get less and less as you go farther away. But this distinct band-like pattern of dots is very curious. And the question is, why do we see this very strange pattern of dots? The pattern of dots resembles what you would find if you were sending not particles through the apparatus, but waves instead. Now, the way that we explain this experiment today is we say, well, an electron is mathematically described in terms of its behavior using what's called a quantum state. And in this particular kind of experiment, the kind of quantum state that describes an electron, this so-called Schrodinger wave function, behaves in mathematical terms very much like a wave. And because it behaves in many ways like a wave, it mathematically predicts there are certain places where this mathematical wave concentrates, where wave crests or wave troughs add together and you get stronger intensities. And these, because of Born's statistical interpretation, are places where you're more likely to find the electron. And then there are places where a crest and a trough of the wave, an up part and a down part of the wave, cancel or destructively interfere. These are places where the net wave is very weak. And again, by Born's statistical interpretation, these are places where you're unlikely to find the electron. And so the laws of quantum theory, and in particular the mathematical laws of wave development, predict through the second principle that I listed there on that earlier slide, the principle that tells us how to take a quantum state and predict measurement outcomes. It predicts that when we measure where the electron is going to be, that is when the screen detects its location, places where the quantum state has a stronger value are places where you're more likely to find the electron. And again, because of the mathematics of wave interference, we find the electron more likely to be found at some places than others. But the double slit experiment is also a really important opportunity to point out that trying to think of particles as literal physical waves in physical 3D space is actually very problematic. I said that for a single electron sent in at one at a time, it's very convenient to think of the quantum state as a physical looking kind of a wave, but it really is not a physical wave, and it doesn't live in physical space. If you consider more complicated systems, for example, if you send pairs of electrons in at a time, the quantum state doesn't look like a wave in physical space at all. In fact, the quantum state looks, to the extent it looks like a wave, it looks like a wave moving around in a 6-dimensional space. Each electron has 3 coordinates. Each electron has an XYZ coordinate. There's 2 electrons. And so the wave function is actually a function of 6 coordinates and moves around in what looks like a 6-dimensional so-called configuration space. If you send 3 electrons, then the wave function lives in 9-dimensional space. And in general, if you send n, where n is some integer number of electrons, it lives in a 3n-dimensional space. And this picture, this familiar, intuitive picture of waves moving around becomes a little murky. And for other systems, there aren't even well-defined waves at all. So although using waves does give an intuitive way to understand why a single electron going through this apparatus produces that pattern, the usefulness of this picture becomes decreasingly helpful as you consider more and more complicated systems. And in general, the only explanation I can give for why we get the kinds of interference patterns we get in the more general case, when you're not just sending one electron at a time, but maybe many, or maybe more complicated systems, is just to say quantum theory is murky. The rules of quantum mechanics are very abstract mathematical rules, and they predict what we'll get with measurements. And oftentimes we don't have a clear physical picture as to why that is going on.
Thank you so much. Any other questions from the audience? I've got one back here. Okay.
Hello. Do you have a YouTube, Instagram, TikTok, or something like that you explain more information?
Yes. Just Google my name, Jacob Barandes, and YouTube, and you'll find a lot of content there right now. Yeah. So please feel free.
Thank you so much. I'm sure we can, we've shared Dr. Barandes's information on Instagram, so you can find his name on there. We're going to say goodnight to you now. Jacob, thank you so much for joining us. We'll see you
Good night,
next
everybody,
time.
and enjoy the film.
Thank you.